So if this is A here, this is set X in Venn diagram terms. So if this is your X, and you've got an A here and a B here, two members of X, and they map to the same point, the same value. Let's say f of A. So that's A, that's B. So f of A will be here, and f of B will also be here. Okay. So now the question is this mapping f of A equals f of B. That relation, this tilde here, is it an equivalence relation? Is it of that special kind? Well, f of A obviously equals itself, right? So that means A tilde A. So if you had a B here, you'd have a B here, right? So we've substituted for, instead of B, we put A. So f of A equals f of A, and hence that's true, right? A tilde itself. So A is equivalent to itself. So it's reflexive. This relation here is reflexive, right? A tilde A, right? Now, how about symmetric? We're testing for to see if this relation here is an equivalence relation. You know, does it satisfy those three properties? All right. Okay. So if A is equivalent to B, then FA equals FB, but FB is just the same as FA, right? So you're just swapping the A's and B's, so therefore you get B is equivalent to A. So if A is equivalent to B, B is equivalent to A. So this relation here is symmetric, right? That's the second property satisfied. Now if A is equivalent to B and B is equivalent to C, that means that f of A equals f of B, and from here f of B equals f of C, right? Well, if f of A equals f of B and f of B equals f of C, then f of A equals f of C, right? Sort of common sense. Okay, so f of A equals f of C, and that implies, by the definition of the relation, that means that A is equivalent. What's the word? Well, A tilde C. Right? So if A tilde B, B tilde C, therefore A tilde C. So it's transitive. This relation here is transitive. Well, that means it's all three. Therefore, this relation here is an equivalence relation. All right? All right. So let's ask, for this equivalence relation involving functions, what are the equivalence classes? So let's picture it, sort of give a visual impression. Let's say in terms of Venn diagrams, let's say this that's your set X, that's your starting set, all right? And these bars here, 1, 2, 3, all of that is of X. In those subsets, these are subsets, right? And you've got these other subsets as well. All the elements that belong to this subset, they all those points. Let's say f of x, they're all equivalent. So for all these little x's in here, all the elements here, all their f of those elements all have the same value. Right? So f of x1 equals f of x2 equals f of x3, da 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 da. So all your elements here, they all map to one point in your target set, right? So this, all the points that get mapped to from these bands, if you like, that is called your image of f. Right? Remember, an image is just what gets mapped to, right? So this is the set of all your points that are getting mapped to. So it's usually just called the image of f, right? Okay, so now it's these bands, these subsets. They're very important in future work. So they're given a special name. They're given a label in the context of equivalence relations involving functions, because mapping is very basic. So when we're talking about equivalence relations of functions, involving functions, these subsets here, they're given a special name called a fiber, and you can probably see why that was called. I mean, you've got all these mappings, you know, from these subsets to points, so they just sort of look a bit like fibers, right? And how do you weave cloth? Well, you have a lot of fibers, right? Like in a loom, weaving cloth. Right? You've got all these fibers, right? So that's probably where, you know, I'm just guessing, but I'd say it was highly likely. That's why these lines here, these mappings, from a subset to a point. So obviously many to one. Okay. So these subsets here, these bands, these regions, are called fibers. Now look, in anticipating, now I've run out of board, but anticipating a bit of the next session, are you suspicious that there may be a bijective mapping from each band, or each fiber as they're called? And these bands are the equivalence classes, right? Because every member of this band or fiber have the same value. They all map to the same point. So this point here is f of x1, f of x2, f of x3. You know, all these x's here. They all map to the same point. Right? So if they all have the same value, f of xi, whatever, for the xi's here, they're all equivalent, right? So all the members of this subset are equivalent, and that's the definition of an equivalence class. Okay, so in this context, these bands are the equivalence classes. So in here you've got 3 different equivalence classes. Now you have more, and remember the theorem that any set like X is a disjoint union of equivalence classes. So I mean, I've just drawn 3 bands here, but you'd have the whole set all mapping to different points. Okay, so the conjecture now is this mapping between fibers, well, a set of fibers. So you've got what, three drawn here. So is there a bijective mapping between the fibers and this set, the image of F, right? This target set? So the question, you know, is this so here's a mapping that maps the set of fibers. This one, this one, this one. So this mapping that maps the set of fibers into the points, well, the set, well, in other words, just the image of F, right, the set of these points. That mapping, call it theta, that maps the set of fibers into the set of these points. You're mapping it from a set to a set. That mapping, is it bijective? Now the next theorem, I've run out of board, but it'll be theorem 57, and it will prove that this mapping is bijective. And we will come across this again in the last chapter, so 3 lectures away from now, in theorem 64. Now, so I'll finish this off. I'll do 57 next session, and probably combine it with the problem-solving session. Now, I think there are only two questions in there are only 2 exercises at the end of the chapter of chapter 16, but they're multi-parts. Like question 1 has five parts to it, 5 questions, and question 2 has 11. So effectively there's 16 questions, I guess. I'll do about a third or a half. So I'll probably combine the proof of this with the problem-solving session next time.